Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 31st, 2025, just about 5 days ago. It introduces a new monocular dense SLAM system that integrates depth foundation models to fix geometric inconsistencies in prior work, achieving state-of-the-art tracking accuracy while running in real time at 18 frames per second. The paper is titled FoundationSLAM: Unleashing the Power of Depth Foundation Models for End-to-End Dense Visual SLAM. And as we'll see later, the improvements in both trajectory estimation and reconstruction quality are really quite striking. Figure 1 illustrates these gains with a radar chart comparing the new method against leading baselines like DroidSLAM and MasterSLAM. The plot tracks normalized errors across several benchmarks, including Euro C, 7 scenes, and TIUM RGBD. Since the center represents zero error, the text explicitly notes that lower is better. Consequently, the orange star line, which hugs the center much more tightly than the green or blue polygons, demonstrates that FoundationSLAM consistently achieves the lowest trajectory error and reconstruction distance across all tested scenarios. Alright, Figure 2 details the system architecture that makes those results possible. The process begins on the left with the hybrid flow network, which fuses features from a foundation depth model to inject structural awareness. Then, in the central green block, the reliability-aware flow refinement takes over. This module uses a flow GRU to update predictions, distinguishing between reliable regions that use local searches and unreliable ones that rely on global priors. Finally, the bi-consistent bundle adjustment layer on the right jointly optimizes depth and pose by enforcing both flow and geometry constraints. Algorithm 1 breaks down the specific logic for this refinement process. The key innovation appears in line 2, where the computed correlation volume is multiplied by a reliability mask, M sub I. This step filters out noise from unreliable regions before the data reaches the feature aggregator in line 3. Finally, lines 4 and 5 use a flow GRU to calculate the incremental update, delta F, ensuring that the new flow estimate remains geometrically consistent. So, having defined the refinement strategy, we can verify its impact on real-world metrics. Table 2 details the tracking accuracy on the Euro C dataset, where the columns cover various recording environments, like machine hall and Vicon room. The rows compare the new method against state-of-the-art systems, including DroidSLAM and MasterSLAM. FoundationSLAM, shown at the bottom, consistently achieves the best performance. It reaches an average error of just 0.019, beating the nearest competitor on challenging sequences like V203. Well, Figure 3 brings those metrics to life with a qualitative comparison on the TNT dataset. The left side shows the baseline MasterSLAM, while the right side displays FoundationSLAM. Note the vertical labels indicating that the new method runs at 18 frames per second, which is nearly double the speed of the baseline. In the detail columns, we see that FoundationSLAM produces sharper geometry with fewer artifacts. Finally, the keyframe plots on the far right of each block show that the system maintains significantly more keyframes, ensuring better geometric consistency. Okay, Figure 5 now isolates the impact of the bi-consistent bundle adjustment layer across different datasets. The top row provides the RGB reference images. In the second row, DroidSLAM struggles with distinct artifacts, marked by the dotted boxes. The third row shows the proposed method without the bundle adjustment, which still suffers from some inconsistencies. By contrast, the fourth row incorporates the full bi-consistent layer, delivering smooth, high-quality depth maps that align closely with the ground truth at the bottom. To quantify exactly how much each piece contributes, Table 6 presents an ablation study on the Euro C dataset. The first 3 columns track the inclusion of the bi-consistent bundle adjustment layer, labeled BI-BA, along with the node-wise and edge-wise reliability masks. As we read down the table, adding these mechanisms individually clearly helps, but the bottom row confirms that the full model works best. By combining all 3 elements, the system achieves the lowest trajectory error and a chamfer distance of just 0.048. Wrapping up, 2 takeaways stand out. FoundationSLAM successfully injects geometric awareness into flow-based systems, and it does so without sacrificing speed. This implies that future real-time tracking will likely depend on strong priors from foundation models to resolve structural ambiguities. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.